Hey everyone! If you're building on AWS, or maybe you're cramming for that Developer Associate exam, then you have to know event-driven architecture inside and out. So today, we're going to break down the absolute bedrock, the foundation of it all, SNS, SQS, and the super powerful Fanout pattern. Ready? Let's dive in. You know, so many applications start out just like this. It's the classic monolith, right? You've got all your features, the user service, the shopping cart, the accounts. Everything is just jammed together in one big, tightly coupled code base. And it's usually all pointing to one single massive database. I mean, it seems simple at first, but trust me, that simplicity, it's a trap. Because think about it. What happens when you just want to update the card service? Well, you have to redeploy the entire application. You risk breaking something totally unrelated in the user service. Or what if the account service gets a huge spike in traffic? You can't just scale that one piece. Oh no, you have to scale the whole thing. It's so inefficient and it gets expensive fast. Your ability to innovate just grinds to a halt because every tiny change feels like this massive, risky project.
And that leads us to the big question, the one that keeps developers up at night. How do you break free from this without breaking everything in the process? I mean, a complete rewrite from scratch? That's a massive risk. You can't just shut down the business to rebuild. So how do you modernize, but do it safely, step by step, without your users even noticing?
Well, the answer is this absolutely brilliant strategy called the Strangler Fig Pattern. It was famously named by Martin Fowler, and the name is perfect. The whole idea is you build your new, shiny system around the edges of the old one. It literally grows over the old system, and eventually it just strangles it out of existence. It's an awesome, low-risk way to modernize, piece by piece.
Okay, so here's how it actually works in practice. First, you stick a proxy in front of your old monolith. Think of it like a smart traffic cop. To start, it does nothing special. It just passes all the requests straight through to the monolith. But then, let's say you build out a new, independent user service. Now you can tell that proxy, hey, from now on, any traffic related to users, send it over to my new microservice. And the best part, everything else just keeps flowing to the old monolith. No one's the wiser.
And this right here, this is the beautiful end state. Over time, you just keep carving off more and more functionality, piece by piece. The proxy gets smarter and smarter, routing more traffic to your new services until, finally, there's nothing left for the old monolith to do. You can just turn it off. How cool is that? And what you're left with is this beautiful system of independent, scalable, and loosely coupled microservices. Okay, so that's great. But now you have a new problem, right? How do all these new microservices talk to each other without just creating the same old spaghetti mess we wanted to escape? And that is where the publish-subscribe pattern, or pub/sub, comes into play. It works like this. A publisher, say your order service, shouts a message, like an order was created, into a central channel or topic. The key is, it has no idea who's listening. It doesn't care. Then, on the other side, you have subscribers that can choose to listen to that topic and react to the message. They are completely decoupled. This is the secret sauce.
Now, one of the most powerful ways to use pub/sub is what we call the Fanout pattern. Just imagine it's Black Friday. An order gets placed. Your order service publishes one single order-created message. That message is then instantly fanned out to a whole bunch of different destinations at the exact same time. The inventory service gets a copy. The shipping service gets a copy. The analytics team gets a copy. They all process it in parallel. And get this, if the shipping service happens to be down for a minute, who cares? It doesn't stop the inventory service from doing its job. That's what we mean by resilience.
Okay, so let's talk about the tools. How do we actually build this on AWS? Well, for this pattern, you really need to know two core services. Amazon SNS, which is the simple notification service, and Amazon SQS, the simple queue service.
Let's really nail down the difference here, because it's important. I want you to think of SNS as a TV broadcaster. It pushes a signal out to potentially millions of subscribers all at once. It could be an email, a text message, or another application. It just broadcasts. SQS, on the other hand, that's more like a super durable mailbox. Producers drop letters, messages, into the queue, and then consumers come and pull the messages out whenever they're ready to work on them. That's the fundamental difference you have to remember. SNS is push, SQS is pull.
All right, exam time. Here's a scenario you'll definitely see. You've fanned out a message from SNS, but not every subscriber cares about every single message. For example, an order shipped event probably doesn't need to go to your inventory queue, right? So how do you control that? How do you make sure the right messages go to the right places? The answer, and please remember this for the exam, is SNS, Subscription Filter Policies. This is a game changer. It lets each individual subscriber tell SNS, hey, I only want messages that look like this. And the best part is, the filtering happens on the SNS side before the message is even sent. This is super efficient, it saves you money, and it means your back-end services don't waste time in CPU cycles looking at messages they're just going to throw away.
And here's what it actually looks like in practice. It's just a simple little chunk of JSON that you attach to your subscription. This one is basically saying, hey SNS, only send me messages if they have an attribute called event type, and the value is either order.created or order.updated. Any other event like order.shipped, this subscriber will never even see it. It's simple, it's powerful, and I can almost guarantee you'll see a question about it.
Okay, so here's a major exam tip. If you see a question that talks about sending notifications to a massive number of different endpoints, and especially if it mentions things like mobile push notifications, email, or SMS, your brain should immediately just scream SNS. That is exactly what it was designed for. High throughput, fan-out, person-to-person messaging. All right, so we've covered the broadcaster. Now let's dig a little deeper into SQS. Because while SNS gets the message out, SQS is what gives our system the durability and control to make sure everything is processed reliably.
SQS actually comes in two main flavors, and you absolutely have to know the difference. First, you have standard queues. Think of these as the workhorse. You get nearly unlimited throughput and at least once delivery. That means AWS guarantees your message will be delivered, but the order isn't guaranteed, and key point, you might occasionally get a duplicate. Then you have FIFO queues, first in, first out. You use these when the sequence of events is critical. They give you strict ordering and exactly once processing. No duplicates, period.
And here's the trick to making that FIFO ordering actually work. This is another one of those critical exam details. When you send a message to a FIFO queue, you must include a message group ID. Think of it like a conversation ID. All messages with the same group ID are processed in the exact order they were sent. If you forget that message group ID, you get no ordering guarantees. It's that important. So let's talk about a really clever SQS feature, the visibility timeout. This is how SQS stops two different workers from grabbing and processing the exact same message at the same time. Here's the flow. Number one, your worker pulls the queue and receives a message. But SQS doesn't delete it right away. Instead, step two, it just makes it invisible to everyone else and starts a timer. That's the visibility timeout. Step three, your worker has that amount of time to process the message. And finally, step four, if it succeeds, it tells SQS, I'm done, you can delete it now. If it crashes or fails, the timer runs out, the message becomes visible again, and another worker can pick it up. It's a fantastic system for preventing duplicate work. Okay, let's hit a few more rapid-fire facts you need to have in your back pocket for the exam. First up, raw message delivery. If you check this box on an SNS subscription that's pointing to SQS, you get just your message payload, no extra SNS metadata. It can really simplify your code. Second, message deletion is final. Once your consumer deletes a message, it's gone for good. Poof. Third, if you need to delay all messages going into a queue, you set the delivery delay attribute directly on the queue itself. And finally, let's hammer this home. Why can't you use a standard queue for exactly once processing? Because it's at least once delivery, which means duplicates are possible. For exactly once, it has to be FIFO. And don't forget the numbers. They love to ask about limits on the exam. So, what's the maximum message size for both SNS and SQS? The answer is 256 kilobytes. That's it. If you have something bigger, you can't just stuff it in the message. The standard pattern is to drop the big file in an S3 bucket and then just send a message that contains a pointer, a link to that object in S3.
Okay, let's bring it all home. We're going to do a super fast review, your personal cheat sheet for the DVA-CO2 exam. These are the things you absolutely must remember.
First, if you need to filter messages so they only go to certain subscribers, the answer is SNS Subscription Filter Policies, which work based on message attributes.
Next, if the question screams guarantee order or exactly once processing, your answer is SQS FIFO Queues. And don't forget, you must use the message group ID.
And finally, to prevent two consumers from processing the same message at the exact same time, the mechanism you rely on is the SQS visibility timeout. And there you have it, a solid foundation for building and, more importantly for the exam, analyzing these event-driven systems. But it always leads to the next challenge, doesn't it? So here's something to chew on.
Now that your services are all decoupled and reliable, what's the next bottleneck you need to solve? Thanks for watching.